Hi, this is Mr. Yeager with for physics. I'm looking at both momentum and impulse today, and this is a pretty brief lecture. We're going to go ahead and start moving through it. Okay. So, momentum and impulse. What these are going to look at is this is the part of physics that basically involves collisions. What happens when things collide into each other? What happens when you hit another object? How can you calculate object speed, the force involved, how far they go, and so forth. There's all different things that occur with these. So momentum and impulse is a very strong topic, definitely used during collisions. Describes how collisions occur. All right. So we start off with this, basically saying, all right, let me get this out of the way for you. Okay. We know it's going to be, you need more force to stop a faster pitch, a 95-mile-per-hour pitch, versus one that's thrown at 45 miles per hour, because they have, even though they have the same mass. Okay, one's moving faster than the other. Okay, more force is needed to stop a train moving at 45 miles an hour versus a car moving at 45 miles per hour, even though they have the same speed. And so obviously these statements are basically trying to get to the point of, hey, both mass and velocity is what's going to be important to consider when we want to change the motion of the object. Mass and velocity is what's going to be needed to understand, to figure out the force needed to change the motion. That's underlying the key things here. Changing the motion of the object from one state to another state. Okay, so both mass and velocity. All right, and so this mass and velocity, mass times velocity, is called momentum. Okay, it's called momentum. And so we have our basic formula here. Momentum, which is denoted P, equals mass times velocity. All right. Now there's no new special unit for momentum. All right. What we'll usually see happen is we just simply combine the units for mass and velocity. So momentum is measured in kilograms times meters over seconds. That would be the unit for momentum. There is no new unit. We just combine all the units involved to calculate it. All right. But these are the two things that's going to determine the momentum of the object, how much inertia it has. All right. We'll just move forward. That's it. Good. All right. So, a couple more things about momentum. It's mass and velocity, but it's also a vector. Okay? It's a vector, so it has direction. Something that has a momentum north is not the same as something that has momentum to the south. We would say they have different momentum. Okay? So it is a vector quantity. It has magnitude and direction to it. All right? We can change an object's momentum by either changing its mass or velocity. Obviously, for our purposes, we're usually going to change the velocity of the object. All right? When a truck accelerates, the truck doesn't change its mass, it changes its velocity. So that's going to be usually the more important part of this. All right? The thing is, if we're changing the velocity of the object, we are accelerating it, which means a force must be applied. All right? And so therefore, a net force will help cause a change in momentum. So this is a kind of a crazy unit because we're going to put all these old things together. We're putting mass and velocity, motion, kinematics, with force, and we're going to see obviously how this all changes together. All right. So again, we're saying when we change an object's momentum, we change its velocity. A change in velocity is acceleration. If we accelerate, we are applying a force. All right. All those things kind of lead logically from one to the next piece. All right, so a force will help cause a change in momentum. And so that leads us to how Isaac Newton wrote out the Newton's second law. He didn't actually write it as F equals, or F net equals m times a. That's how we know it, F net equals m times a. Instead, he derived a as the change in velocity over time, which that's what acceleration is, a change in velocity over time. All right? And so based on this, if I start kind of manipulating, put the m up top, look at this. Mass times change in velocity, that's change in momentum, which I have written right here, the change in momentum. Okay? And so a force, a net force, if I write it down over here, will cause a change in momentum over time. And so what Newton actually did is he multiplied time out of the denominator, as you see here. So we have force times time. We usually just ignore the delta t, but the delta symbol. So usually it's just F times t, force times time, will equal mass times change in velocity, which equals a change in momentum. So a force applied over a period of time will create a change in momentum. And this force times time is called impulse. All right, is called impulse. So we say an impulse will cause a change in momentum. All right. So some of the tricky things that might pop up is I might say find the change in momentum if I say the force is 10 newtons and the time is 2 seconds. Find the change in momentum. I've had students in the past tell me, well, I can't find change in momentum. Change in momentum is mass times velocity. I go, what did I give you? And they go, you gave me impulse. The impulse is 20. I can give you the impulse, 20 newton seconds. All right. But I don't know what the change in momentum is. Well, I go, well, think about it, guys. What does an impulse cause? A change in momentum. So what did you solve? You found the change in momentum. All right. So that's going to be the only real tricky part about this particular unit is to realize, you can see all the arrows over this. I'm going to go and erase it. That, hey, even though from a definition standpoint, a change in momentum is mass times delta V, I can also calculate it by finding the impulse. They're all the same. Okay? So an impulse is the product of the force times the time that it is exerted. Okay? Force times time. So that's the official definition of impulse. All right? But it causes a change in momentum. So impulse is change in momentum. All right? The impulse will cause the change in velocity, the change in momentum of the object. All right? This is a pretty straightforward statement. Obviously, with the greater the impulse, the greater change in velocity. Okay? The increase in force will increase, and the amount of time will obviously cause the greater change in velocity. If I increase force and time, force times time is impulse, which will cause the greatest change in momentum. Okay? And obviously, in this way, velocity. All right? So that gets us to one of our first little problems here. All right? A 1,000 kilogram car moving at 30 meters per second can be stopped by a 30,000 newton force acting for 1 second. How did we figure that out? 1,000 times 30 is 30,000. That's what's stated at the very top there. Let me get my pen back. Okay? 1,000 times 30, mass times velocity, is 30,000 kilograms meters per second. All right? I want to change that momentum to a stop, which means P equals 0. All right? If you're not moving, you have no velocity, you have no momentum. I can change that by doing 30,000 times 1 second. That's a huge force. You don't want that much force being applied against you. That would be a crash. It's more likely that you'll apply a lighter braking force of 3,000 newtons over a longer period of time and be able to stop just as well. Obviously, you're going to need more distance to stop because it's taking longer. All right? So the outcome might be different, but this is the same impulse. 3,000 times 10 seconds, 30,000 times 1 second. Both are the exact same impulse. Both are the exact same change in momentum, but we could have a different outcome. One is a crash, one's a quiet stop. So that's, again, another tricky thing about this. All right. And so that leads us really to our last big formula for momentum. This is a very short unit in terms of the notes. Okay? If we only look at a closed system, as is stated, and we're only going to look at closed systems, basically the objects involved, momentum will always be conserved. I'm going to adjust this a little bit. What we usually like to say instead of P1 and P2 is the initial momentum of the system will equal the sum of the final momentum of the system. All right? what we're looking at here, and we're going to do a problem in just a moment, and you're going to get lots of other practice as well, all right, is the overall momentum before a collision, before a occurrence, an action, will still be the same amount of momentum. The same amount of momentum will still be there after the action. And again, we're looking at right before and right after the action. Okay, it's an instant. That's the thing. Obviously, once you start moving farther away, friction might get involved and all these other things. We don't want to pay attention to that. I want to know what's happening right before and right after the collision or the action that takes place. The momentum before and after must be the same. And so what you can see we're going to do here is, depending on the number of objects, if you have only 2 objects, what's the momentum of the object initially? What is their initial velocities for each object? We can get rid of the third one. What's their final velocities on the other side? They can change, but the sum of them must equal the sum of the initial amount as well. The law of conservation of momentum is always true in the problems we are going to do. Okay? So we have this problem with the kangaroo. All right, I'm going to get to the point of it right here, basically. Okay? The kangaroo is sitting on a log. So how much momentum do they have? 0. And I'm going to write this all out. There is no momentum initially. Okay? Which means, what should be the sum of momentum at the end? 0. All right? But the thing is, the kangaroo gets scared. It jumps off the log with a velocity of 15 meters per second. The log moves 3.8 meters per second away from the bank. All right? Equal opposite reactions occurring here. Newton's third law. If the mass of the log is 250 kilograms, what's the mass of the kangaroo? Okay? So, what does this mean? I'll go back to here and draw it all out for us. Okay? What you have here is you have your log on water. Okay? I can't draw a kangaroo, so I'm just going to draw like a box. Okay? This is my kangaroo. Sorry for my terrible drawings. Kangaroo. All right? And so what happens is the kangaroo jumps towards the shore. Well, if the kangaroo pushes towards the shore, that means the log will go back. All right? And the thing is, momentum before and after this jump must be the same. Well, let's look at this. Initial momentum, final momentum. Well, I only have 2 objects. I have the log mass and I have the kangaroo mass. Okay? And so what I can do here is I can go, okay, this is the mass of the kangaroo times its initial velocity plus the mass of the log times its initial velocity will equal the mass of the kangaroo times its final velocity plus the mass of the log times its final velocity. Well, the thing is, all right, what's the initial velocity of the kangaroo and the log? It's 0. 0 and 0. So what is my overall initial momentum? It is 0. There is no momentum initially, which means, what must my 2 momentas add up to afterwards? The answer is 0. They have to add up to 0. Well, how can that occur? It's because momentum's a vector. We will say the kangaroo maybe is positive while the log is going negatively. And so if I rewrite this out, I get mkvf. I'm going to write minus mlvl because it's going to be a negative velocity. If I put it to the other side, I just set the 2 momentums equal to each other. They must have the same magnitude momenta, but obviously opposite directions. And now I can plug everything on in. So my mass of the log, 250 times 3.8 and 15. 250 times 3.8 will equal mk, the mass of the kangaroo, times 15. That's a pretty simple equation to solve for. The mass of the kangaroo will come out to be 63.3 kilograms. All right? So that's showing you how the conservation of momentum principle. All right? This is one type where the objects don't move and then they jump. We could obviously do the opposite where they are moving and they crash and come to a stop. That's another possibility. That just means the momentums of the two objects must be the same. We could also do other problems where maybe the objects keep on moving, and I'll do other videos showing that. Okay? So I think we're wrapping it up here. All right. This leads us to our last concept. All right. This is something that you'll check afterwards. There are two types of collisions that occur, and we call them elastic or inelastic. All right. An elastic collision, the official definition is that momentum and kinetic energy will be conserved. Now, we usually connect momentum and kinetic energy because momentum is mass times velocity. Kinetic energy is 1/2 mv squared. Hey, so that means if I have mass and velocity, I can solve for both momentum and kinetic energy. If they're both conserved during a collision, we will call it an elastic collision. This only possibly occurs. There's actually no such thing as a perfectly elastic collision. We will have to make an ideal problem. It'll possibly only occur when the objects bounce off of each other. They cannot collide and stick together. They have to bounce off. The best example is usually like a tennis ball being thrown into the ground or a bouncy ball being thrown into the ground. It's almost essentially elastic. Inelastic, only momentum is conserved. So momentum's always conserved. How are you going to confirm that kinetic energy is not conserved? You're going to have to calculate it. You're going to have to calculate the initial kinetic energy of the system. How do you do that? Add up all the kinetic energies. Add up the kinetic energies afterwards. See if they're equal. That would be inelastic. All right? So momentum is still always conserved, but the kinetic energy is not. And energy is lost somewhere. This will always occur when objects come to a stop. Okay? That means it's an inelastic collision when they both collide. Or when the objects do what's called couple. You'll see this a lot. That means that the objects collide and stick together. When this occurs, you have an inelastic collision. All right? You know that for sure. That's the nice thing. It's easier to identify inelastic than it is to actually identify elastic. Again, elastic is very, very rare. So this is an extra thing you might do. You might solve the problem, and then it might say, is this elastic or inelastic? Calculate the kinetic energy. And that's it. Thank you.